So today I'm going to be presenting our work on electrical flows over spanning trees, and this is joint work with Swati Gupta, Ali Kodabaksh, and Evdokia and Nikolova. So this is the outline for my talk today. I'm going to introduce the problem, talk about different algorithms that we propose, present some computational results, and finally conclude. So electricity distribution networks are built as sparse grid-like networks, as you see in this figure here, but they're operated as radial networks. So these networks contain switches that literally turn edges on and off in the graph so that only an acyclic subset is operating. And this acyclic subset constraint is a practical requirement that's needed for security reasons. These networks also contain a root node that supplies power to other nodes or end consumers in the network through low voltage power lines. But the problem is that transmission of electrical flow through these low voltage power lines accounts for 10% of the total power loss in the process, and this is a high number, so it's important to find the best acyclic subset to operate so that you minimize the power loss due to transmission. So this brings us to the following optimization problem where our objective is to minimize the total power loss or the energy of the flow subject to flow conservation constraints and the acyclic support constraint. So let's make this more concrete with an example. We have the following grid. The root is this blue node in the top left corner, and all demands and resistances are 1. Upon solving this optimization problem, we end up with the following optimal spanning tree solution. And we can assume in general that the optimal solution forms a spanning tree without loss of generality. And using this observation, an equivalent view of this problem is minimizing this quadratic objective over vertices of the flow polytope. In particular, when all the resistances are 1, then this problem amounts to finding the vertex with the smallest Euclidean norm. And this problem was shown to be NP-hard. So this problem has been looked at since 1989. People have proposed many different heuristics, but no one was really able to offer any provable guarantees. Kodabaksh and al. In 2018, they proved NP-hardness, and they show that they give yet another view of the problem as minimizing a supermodular function subject to a matroid basis constraint. And inspired by that, they propose a branch exchange algorithm that moves from spanning tree to spanning tree. This has really nice computational performance, and it's the go-to algorithm in practice, but it can have exponential running time, I'm going to talk about that later in the talk. In the theory of electrical flows, approaches like spectral sparsification do not extend our case because to compensate for edge deletions, they change the weights on the edges. Also, results on minimizing convex functions over integral points in polytopes and vertices of polytopes also do not extend to our case. So the first step at trying to tackle this problem, suppose we relax the acyclic support constraint. Then the problem reduces down to computing as what's known as an electrical flow in a graph. So back to our example, if we compute this relaxed flow, we get the following solution, and here we see that the solution is far from acyclic. The quadratic objective will try to disperse the flow as much as possible, so it will pick as many edges in its support as it can. And we also have instances on planar graphs where the gap between the flow relaxation, the optimal spanning tree, is omega delta, where delta is the maximum degree, and this maximum degree can be omega n. So the flow relaxation by itself does not do well, but then we propose this iterative rounding algorithm that rounds this flow relaxation value flow relaxation solution to a vertex of the flow polytope. And to do that, we need this notion of effective resistance. So for the effective resistance between a pair of vertices U and V is the potential drop between U and V upon sending 1 unit of current from U to V. So let's parse this with an example. So consider this basic graph where all the resistances are 1. Then if this is your U and V, upon sending 1 unit of electrical flow, this is the relaxed electrical flow here. And the effective resistance is just the flow on this UV edge, which is 1/3. And if we normalize the effective resistance with the resistance, it's 1/3. And here, because the resistances are 1. In this case, this ratio is small because U and V are well connected through disjoint paths. So the quadratic objective is able to disperse the flow through these disjoint paths. On the other extreme end, if this is your U and V, this edge is a bridge. So when you try to send 1 unit of electrical flow, in this case, all of that flow will go through that edge. And in this case, the ratio of the effective resistance to resistance is 1. And you can show that this happens if and only if your edge is a bridge. So this is essentially a bad case, and this is a good case. So we want to be in this case over here. And this is the intuition behind our metric of edge sparsification, where we want to delete edges that have a small effective resistance to resistance ratio. So this brings us to the RIDE algorithm. Algorithm is very simple. At each iteration, it computes the effective resistance for all edges in the graph. This can be very efficiently computed and maintained. And then it deletes an edge with the following probability distribution, where the metric of effective resistance I was talking about appears in the numerator. So this sampling approach ensures that one, the connectivity of the graph is maintained throughout, and two, that edges that are cheap to delete are more likely to be deleted. What I mean by cheap is that edges that upon deletion does not increase the objective function by much. We can show then the following theorem that says that RIDE has an OM minus N approximation with respect to the flow relaxation. It's imperative to note that this is with respect to the flow relaxation, not the optimal spanning tree, and the flow relaxation is a very loose lower bound. As I previously discussed, this becomes an ON approximation for planar graphs, and this is essentially optimal with respect to the flow relaxation. Like, you cannot do better than that. So with the aim of improving the approximation factor of RIDE, we propose this layered matching heuristic. We're able to prove very nice approximations for this heuristic in special cases, such as when we have grid graphs. But in this talk, I'm going to present this heuristic in its most general form. So the heuristic is as follows. So at each iteration, so the heuristic starts by computing a breadth first search tree rooted at the root. And then this partitions the nodes of the graph into different layers depending on their hop length. And then the algorithm starts from the bottom up, and at each iteration, it builds a spanning tree between two consecutive layers. In particular, it matches every node in the lower layer to exactly one node in the above layer. And this is done by solving an MIP that tries to make the flow in this cut as balanced as much as possible. And this local MIP runs very quickly. So let's understand this more with an example. So consider the following graph. The root node is the blue node. We already have the partition of our nodes here into different layers. So first we compute the flow relaxation. We get the following fractional solution. We start from the bottom. We have these two layers. In this case, there's only one possible matching. So we're going to take that edge into our spanning tree. Then we contract these two nodes into this green node that has a demand of 2, because all demands are 1 here. Now we want to again find the matching between this node and the node in the above layer. And now we're going to solve an MIP that minimizes the L infinity norm between the cost of an edge I take in the matching versus the flow of that edge in the relaxed solution. In this case, the 0.88 has the highest flow value, so I'm going to take that in the matching. And so I end up with the following spanning tree. In this case, this is actually the optimal spanning tree. So some computational results. We constructed experiments on sparsified random grid graphs. So this is an example of sparsified grid graph, and this is our abstraction of distribution networks. So this table summarizes the results. So in the first column, we have we benchmark the depth performance of depth first search trees, and this is essentially to show that the problem is highly non-trivial and random spanning trees can actually have arbitrarily high cost. Now I'm going to focus on comparing the performance of RIDE and LM heuristic with the branch exchange algorithm. So if we focus on the last row and the sparsification probability is 0.2, we have the following grid graph. We have the following graph. On the y-axis, we have the optimality gap. On the x-axis, we have the wall clock time. Here, the dotted blue line shows the performance cost of LM heuristic, and the orange dotted line shows the time it takes for the LM heuristic to attain the same cost. Here we see it's around 35,000 seconds, and this is an 0.10 to the 5 speed up. Also, we see that the RIDE is in practice much better than the theoretical approximation factor that we proved. We also see that overall the algorithms run very quickly, and this would allow practitioners to reconfigure networks more often in practice and hence save more money. Finally, to conclude, we considered the network reconfiguration problem and looked at the natural flow relaxation. We proposed the RIDE algorithm, which is the first polynomial time algorithm with any form of proof of guarantees for this problem. We also looked at the LM heuristic and looked at its computational performance. There are many open questions that remain, such as obtaining better lower bounds using electrical flows, or analyzing an iterative deletion algorithm that deletes the edge with the smallest relaxed flow value, as opposed to using the effective resistance as a metric of edge deletion. Thank you.